Good day everyone. My name is Joylyn A. Zapico, a BSCE4A. In this video, we will talk about rectangular components of velocity and acceleration. So for our today's objective, students will be able to relate kinematic quantities in terms of the rectangular components of the vector. But first, I am going to discuss what is rectangular components. So rectangular components are the parts of a vector resolved into vertical and horizontal vector. They are also perpendicular to each other. As you can see in this figure, we have 3 arrows and 1 dot that are running around the circle. So the red arrow represents the position, the green dot represents the velocity, and lastly, the pink arrow represents the acceleration. And now, let me draw a graph about an x and y axis of the rectangular components. So these are the x and y axis. Then we have the point P, N, O, and M. There the point A sub y and A sub x. The point sub A. Okay, so as you can see in the graph, we have the point A, and it represents a resultant vector on point O and P. Through point O, it separates two components in x and y direction axis. The two components are point A sub x and point A sub y on vectors point ON and OM respectively. And from point P, draw two lines in x and y axis as PM and PN. Then we can see that we have now the triangle law of vectors that can be applied on a triangle O and P around point of O and P imaw. We can write it as the point OP is equals to point ON plus point NP. Then we have the point A is equals to point A sub x plus point A sub y, where the components of A are A sub x in x direction and A sub y in y direction. Then from triangle O and P, we will find the value of cosine Q and sine Q. So from equation 1, we have the cosine theta is equals to A sub x over A. Then we will have A sub x is equals to A cosine theta. So that's our equation 1. Next is the sine theta is equals to A sub y over A. Then we have A sub y is equals to A sine theta. That's our equation number 2. After that, we will add the equation 1 and 2 and square it both sides. The A squared sub x plus A squared sub y is equals to A squared cosine squared theta plus A squared sine squared theta, and so on until makuha natin do A squared sub x plus A squared sub y is equals to A squared. Then finally, we will write the magnitude of given vector A as A is equals to square root of A squared sub x plus A squared sub y. Okay, so we will proceed to rectangular components of position. As you can see, position are also a part of rectangular components. So rectangular components of position are often convenient to describe the motion of a particle in terms of its x, y, z or rectangular components relative to a fixed frame of reference. So in this graph, the position of the particle can be defined at any instant by the position vector, or the r is equals to xi plus yj plus zk. The x, y, z components may all be functions of time, or the x is equals to x times t, y is equals to y times t, and z is equals to z times t. Then the magnitude of the position vector is r is equals to x squared plus y squared plus z squared raised to 0.5. Then the direction of r is defined by the unit vector, or the u sub r is equals to y over r times r. Next, we have the rectangular components of velocity. So, the velocity vector is the time derivative of the position vector, or the v is equals to v sub x Next is rectangular components of velocity. So the velocity vector is the time derivative of the position vector, or the v is equals to derivative of r over derivative of t is equals to derivative of xi over derivative of t plus derivative of yj over derivative of t plus derivative of zk over derivative of t. In this graph, as you can see in the figure, since the unit vectors I, j, k are constant in magnitude and direction, this equation reduces to v is equals to v sub xi plus v sub yj plus v sub zk, where v sub x is equals to x, then it is equals to derivative of x over derivative of t. Then for v sub y, it equals y, then equals to derivative of y over derivative of t, same as v sub z is equals to z, then it equals derivative of z over derivative of t. And so the magnitude of the velocity vector is v is equals to v sub x squared plus v sub y squared plus v sub z squared raised to 0.5, and so the direction of v is tangent to the path of motion. Next are the rectangular components of acceleration. The acceleration vector is the time derivative of the velocity vector, or the second derivative of the position vector, or the a is equals to derivative of v over derivative of t is equals to second derivative of r over second derivative of t. Then it equals to a sub xi plus a sub j plus a sub z k, where a sub x is equals to first derivative of x, then it equals to second derivative of x, that equals to derivative of v sub x over derivative of t. Then for a sub y, it equals to first derivative of v sub y, then equals to second derivative of y, that is equals to derivative of v sub y over derivative of t. Then same as a sub z, it equals to first derivative of z, that equals to second derivative of z, and it will equals to the derivative of z sub z over derivative of t. Then, as you can see in the figure of the graph, the magnitude of the acceleration vector is a is equals to a sub x squared plus a sub y squared plus a sub z squared raised to 0.5. Then, the direction of A is usually not tangent to the path of the particle. Okay, so that's the end of my discussion about rectangular components of velocity and acceleration. So next, I will give some examples of rectangular components of velocity and acceleration. Okay, so for our example number 1, the box slides down the slope described by the equation y is equals to 0.05 x squared meter, where x is in meters. V sub x is equals to negative 3 meter per second, and for a sub x is equals to negative 1.5 meter per second squared at x is equals to 5 meter. Then, find the components of the velocity and the acceleration of the bow at x is equals to 5 meter. Then, for our solution, first, the first derivative of y is equals to 2 times 0.05 x of first derivative of x is equals to 0.1 x of first derivative of x. Then for the second derivative of y is equals to 0.1 x of first derivative of x plus 0.1 x of second derivative of x. Then we need to substitute it in x is equals to 5 into first derivative of y and second derivative of y. Since x is equals to negative 3 meter per second and second derivative of x is equals to negative 1.5 meter per second squared, so at x is equals to 5 meter, so we'll find the value of our first derivative of y and second derivative of y. So substitute Anton, do x into 5 and first derivative of x into negative 3. Then we will get our first derivative of x is equals to negative 1.5 meter per second. And for our second derivative of y, our final answer is 0.15 meter per second squared. Then so we have now our first derivative of y and second derivative of y. So let's proceed at x is equals to 5. Then kuhain natin ang value ng v sub y and a sub x. So since positive lang ang kailangan, then sa v sub y is equals to negative 1.5, then we will make it as 1.5 meter per second kasi nga kailangan positive siya. So for x For a sub x, we have 0.15 meter per second squared. So that's our final answer. The v sub y is equals to 1.5 meter per second and a sub x is equals to 0.15 meter per second squared. Okay, next for our example number 2. The motion of two particles A and B is described by the position vectors r sub A is equals to 3ti plus 9t times 2 minus tj meter. For our r sub B is equals to 3 times t squared minus 2t plus 2 times I plus 3 times t minus 2 times j meter. So then, we'll find the point at which the particles collide and their speeds just before the collision. So here's our solution. The r sub A is equals to r sub B, then x sub A is equals to x sub B, then y sub A is equals to y sub B. Okay, for our x components, we have 3t is equals to 3 times t squared minus 2t plus 2. Then, arrange natin imo into equation. So we have t is equal t squared minus 3t plus 2 is equals to 0. Then, we will solve it using our formula. T is equals to 3 plus minus times 3 squared minus 4 times 1 times 2 raised to 0.5 over 2 times 1, where t is equals to 2 or 1. Then for our y components, 9t times 2 minus t is equals to 3 times t minus 2. Then we'll also arrange it as an equation. So we have 3t squared minus 5t minus 2 is equals to 0. Then, lipat natin siya into our formula. T squared, t is equals to 5 plus minus times 5 squared minus 4 times 3 times negative 2 raised to 0.5 over 2 times 3, where t is equals to 2 or negative 1/3. Then, to our x sub A is equals to x sub B equals siya sa 6 meter. Then, for our y sub A equals y sub B is equals lang siya sa 0. Then, proceed tayo sa v sub A is equals to derivative of r sub A over derivative of t equals to first derivative of x sub A times I plus first derivative of y sub A times j. Then we have 3 times I plus times 18 minus 18 times t times j, where t is equals to 2. Then, we have 3i minus 18j meter per second. Next, for v sub b is equals to derivative of r sub b over derivative of t is equals to first derivative of x sub b times I plus first derivative of y sub b times j. Then we have 6t minus 6 times I plus 3i, where t is equals to 2. Then we have v sub b is equals to 6i plus 3j meter per second. Then, we will use the formula of rectangular components of position. The r is equals to x squared plus y squared plus z squared raised to 0.5. Then, para makuha natin ang value ng v sub A and v sub B. So, for v sub A, we have 3 squared plus 18 squared raised to 0.5 is equals to 18.2 meter per second. So, for our v sub B, is equals to 6 squared plus 3 squared raised to 0.5. Then we have 6.7 meter per second. So for our final answer of V sub A and V sub B, the V sub A is equals to 18.2 meter per second, and for V sub B is equals to 6.7 meter per second. Okay, and that's all. That's all about my discussion about rectangular components of velocity and acceleration. So I hope that you've learned something about my discussion. So that's all, and thank you for watching.